Hi everybody, this is Mr. Zarzak, and in this screencast I am going to take you through some of the mathematical equations governing right-hand rule number 1. In other words, what can we do with this rule mathematically? Alright, so let's get right to it. Okay, we've got current along a long straight wire, so you can see here I've got the current flowing to the right. That generates a magnetic field that emanates radially around the loop. So you can see like these lines here are just showing the direction of the magnetic field. That's where we would apply right-hand rule number 1, which just tells us the direction. So like if we looked at the magnetic field of the loop right here, when it would be breaking the plane of the screen itself, the direction of the magnetic field would be like coming out of the screen. Okay, over here, the direction of the magnetic field would be down. When that loop is going back into the screen, the magnetic field is back into the screen. Okay, that can be kind of hard to see here. If I snuck a peek back behind the wire, you'd see that the magnetic field back here would be up. You really need to watch the companion video that shows these demonstrated live to get the direction part. But that's really not what we're going to focus on here. Here we're going to focus more on the mathematics. All right, so anyways, the equation for this case of the magnetic field around a long straight wire is this equation right here. Is that B is equal to mu naught I over 2 pi r. Okay, so the B, that's the symbol that we use for the magnetic field. Strength. Okay, and the unit for the magnetic field is the Tesla. Okay, which we just abbreviate as a T. Okay, the Tesla does break down into more base units. We'll hit that another time. This is really not the right equation to see what that is for. Okay, for now, magnetic field is measured in Tesla. Great. This mu naught, this is what's called the permeability of free space. You might remember from electrostatics, we looked at the permeability of free space. That's like our electrostatics constant. That's our epsilon naught, which can be written in terms to get us to Coulomb's constant. You might remember that K is equal to 1 over, what was it, 4 pi epsilon naught. Okay, that's not so important. That's more from previous unit. This mu naught thing, though, that's just our permeability of free space. So that's like our magnetic constant. In other words, the magnetic field B here, okay, is proportional to the current in the wire, okay, divided by 2 pi r. So if you think like 2 pi r, that's just the circumference of a circle. All right, and notice that the radius here is in the denominator. That just tells us that the farther we get from the wire, the weaker the magnetic field gets. Okay, so we've got this proportionality between the current I, this inverse proportionality between the distance r. It makes a circle, the magnetic field does, around the wire. Okay, and then to make the equation work, there is a proportionality constant we call the permeability of free space. This is something that we measure. All right, if you're looking at this for honors, this is the first time you're seeing it. If it's for AP, this is review. This B is equal to mu naught I over 2 pi r is not on the AP equation sheet because you're going to see that it's something that we actually derive later on from a thing that's called Ampere's law. If you're in honors, don't worry about that. Okay, so anyways, so moving right along, this configuration is not that useful because, well, without a really huge current, you can see this permeability of free space is 4 pi e to the negative 7th. So it's a really, really small value. So unless we have a ridiculously large current, we don't get any appreciable magnetic field. And the problem with that is that, well, to get higher currents, you're pushing more charges through this conductive wire, which causes it to heat up. So a lot of times with just like a straight wire, before you get any appreciable magnetic field, your wire's already melted, so it's not very useful. So we have to come up with clever ways to kind of get a boost of that magnetic field. So how do we do that? With loops. Okay, we take our wire and we twist it in a loop. So you can see here I've just taken that straight wire, okay, and I've turned it around on itself. Now this picture is not perfect, so you're gonna have to use your imagination a little bit. Okay, this little bronze gold color loop, this is a perfect circle. Okay, so just play along with me here. All right, imagine the current coming in this way through the wire. All right, and it's going to go in different directions as we move through the wire, kind of like this. So again, I'm just looking at the current. All right, so I'm going to take a look. Oh, and actually, I'm sorry, I take it back. The current's coming in this way. Okay, so scratch everything I just said. The current comes in this way. Okay, and we're going to look at this current at different locations. All right, so I want to zoom in on this. So this current right at this point in the wire would be like pointed this direction. Okay, so from right-hand rule, if the current is up, all right, if I curve my fingers around, hopefully you can see, all right, that the direction of the magnetic field is going to be into this loop, all right? And so I'm going to show that with an X. X means into the page, okay? Now, if we scroll back here a little bit, all right, the magnetic field that we get from a wire is this mu naught I over 2 pi r, which tells us, all right, that the magnetic field gets weaker the farther away we are from the source of the current. So to go back to this, okay, think we'd have very close to this segment, we'd have a very large magnetic field, at least proportionally speaking. Okay, and then as we move farther away, that magnetic field would drop off when it gets smaller, 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 smaller. So I'm drawing these little X's. Okay, it becomes hard to see that they're even X's. I'm trying to show that they're getting smaller the farther away from the wire we are. All right. Now, I'm going to change colors here, okay, just so that we can see the distinction. All right, so like over here, the current in the wire would be the same value, just be pointing this opposite direction. So from right-hand rule number 1, okay, if we curled our fingers around the wire, the magnetic field would again be going into the page, okay, right when it broke the plane of the loop. All right, and for more detailed visuals of that, again, see that companion video on applying right-hand rule number 1. All right, well, anyways, so close to this wire segment, all right, we'd have a very strong magnetic field into the page, okay, just like we did over here, all right, when we were close to that part of the wire. And that would also drop off as we got farther away. So think like my little X's, which is just showing the direction of the magnetic field. Okay, those would get smaller, 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 all right? So anyways, going back to the red side, so the magnetic field gets weaker as we go this way. On the green side, the magnetic field gets weaker as we go this way. All right, and so when we get into like kind of like the middle here, okay, we've got kind of a medium-sized contribution from the magnetic field from the red and kind of a medium-sized magnetic field contribution from the green. And if we added those two contributions up, okay, we get some overall magnetic field that just so happens to be the exact same size as we did over here and over here. And in fact, all right, we got to use a little bit of imagination, but we can imagine that up here, you know, the current's going this way, so we get like big, and then this gets like smaller, 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 and like down here, the current's flowing in this direction, so we get like big and smaller, 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 smaller. This gets pretty messy pretty fast. All right, what I'm getting at is that as long as we stay inside the circle of this loop, okay, the magnetic field that we get is the same size everywhere, and it points the same direction everywhere. Okay, what does that mean? That means uniform magnetic field. Again, as long as we stay inside, okay, the loop, anywhere on this plane, all right, of inside the loop, the magnetic field is the exact same size. All right, and it's only controlled by really two factors. One, how much current do we have going through the loop, and what's the actual physical size of the loop itself? Okay, so again, we got to use a little bit of imagination. Clearly, this is a perfect circle. Yeah, right. Okay, but it's a perfect circle of radius r. Okay, so it's like a fixed radius. All right, so like in AP, remember, we use capital letters for things that are non-variables. All right, and so we wind up with this equation. This is for a single loop, and this just says, all right, look, the magnetic field inside the loop only, not outside, just inside, is equal to this permeability. I get those confused all the time. So the constant, all right, times the current running through the wire, okay, divided by 2r. Okay, notice that the pi has been dropped from this. We'll derive this later. It doesn't matter if the pi's not in there. Okay, what's important is that this r is the radius of the loop itself. All right, so this r is the radius of the loop. Okay, it's not the distance from the wire. It's the physical size of this circle. All right. If we took and continued to wrap our wire around, so in other words, like this is just like a single loop, okay? Well, what if instead of doing a single loop, what if we did a double loop? In other words, what if we did like a loop, and then before we came back out over here, we looped it again over on top of itself? Okay, well, we'd have two loops stacked on top of ourselves. All right, if we could do the same thing with three. We go around, we go loop 1, loop 2, and loop 3 before we come back out. All right, well, if we did that, every time we would loop around, all right, we would get another contribution from the current. In other words, if I took this and I layered a secondary loop on top of the first, okay, it would act like a secondary electromagnet, creating a secondary field inside the loop, all right? But rather than taking a second loop and layering it on top of this first one, okay, all I'm going to do is just wrap it around twice. 1, 2, okay? When I do that, I get a multiplier effect. Okay, so when we have these stacked loops, sometimes these get called a toroid, all right? Let's see, toroid, like that, I believe that's how you spell it. Okay, when you get a stack of loops like that, all right, the fields combine together, all right? And so we get this alternate equation. Now, this alternate equation is really just that magnetic field is equal to mu naught times I divided by 2r, where r is just the radius, okay, the size of the loop itself, okay, but this n, that's just the number of loops. Oops, excuse me. So capital N is equal to the number of loops. Okay, so if I wrapped around 2 loops, so I go around like 1, 2 times, okay, well then n would be equal to 2. If n is equal to 2, well then that would make the magnetic field 2 times as large. Okay, it's just a multiplier. If I instead did 3 loops, 1, 2, 3, okay, well then n would be equal to 3, which would give me 3 times the magnetic field. Pretty useful little trick. All right, so we use that a lot to boost our magnetic field for the same current. We can run the same current through the wire, and if we just run it around and around and around, the more times we want to run it around, every time we do that, we get a boost. We get a multiplier. All right, pretty neat. Now, you can imagine that as we start to stack up more and more of these loops, okay, well, like these are physical wires, all right, and we want to insulate those wires from the other wires so that we don't short across the wires, okay, so the more loops we make, the more space this takes up. And at some point, all right, well, as we start to stack these loops one on top of the next, 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 and so on 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 and so on, okay, it looks less like this kind of toroid shape, which is kind of like a donut, okay, and it starts to look more and more like a cylinder. All right. Eventually, this thing looks so much like a cylinder that we give it its own different name. We call it what we call a solenoid, okay? And this is probably the most common electromagnet. We see these things everywhere. They're in everything from the starter on a motor in your car to inside your doorbell to just like they show up all over the place, okay? This is your common electromagnet. Chances are, if you ever play around when you were younger with like wrapping a coil of wire around like a metal nail, you were building a solenoid. Anyways, the diagram that I have on the screen right now shows what the magnetic field looks like both inside and outside the solenoid. If you were paying attention to permanent magnets, this has essentially the exact same kind of magnetic field layout as a bar magnet, it's like a cylindrical bar magnet. I know that sounds like a contradiction. What's a cylindrical bar magnet? If you had a bar magnet you put it in the shape of a cylinder, this is the kind of magnetic field you would get. Now, with the solenoid, what we're interested in is what's going on here on the inside. That's where the real action is, because that's when we've got a whole bunch of magnetic field lines. All right, the more lines we see, that's an indication of the strength of the magnetic field. Also, look inside the coils and notice that here they're all moving directly to the left inside the field. So what we have is we have a uniform magnetic field, okay, that's strong on the inside. On the outside, okay, it looks kind of like a bar magnet. It's proportionally weaker and it's non-uniform. We don't care about that. When it starts to look like a cylinder like this, all right, the behavior of the thing changes and the equation that we use, it changes too, all right? We wind up with this relationship, okay, where we get this mu naught times n times I. Now, this n is really the key, all right? This is a different n. So we got n over L, where L is the length of the solenoid. So this would be like, so from here to here, that's our L, all right? Excuse me. And the big N is the number of turns that we have in that length, okay? So like this big N, that's still like the number of loops. This would be like number of loops, okay? We tend to call these loops turns. So in other words, it's how many times we've turned the wire around the cylinder. Okay, so just keep in mind that those two terms get used interchangeably. All right, and then we just take the ratio of the number of loops or number of turns divided by the length. So like you're going to see these little n's, okay, this is a big N over L, so you're going to hear things like, oh, well, this solenoid has a loop density of 500 turns per meter. Okay, that's the way that they relate that. So like if it's the big N is just the number of loops. There's 12 loops, there's 50 loops, there's a million loops. Okay, the little n is the loops or the turns per meter. Okay, they'll also write as like n is equal to 500 loops per meter. Okay, both of those are fair game. This is typically the way they'll say that. All right. This equation, this B is equal to mu naught Ni. All right, by this point, okay, you've studied a lot of physics equations. You might remember that we call this one the bunny equation. Okay, why? Because if you look at it long enough and you blur your eyes and you're really, really tired, it kind of looks like it spells the word bunny. Okay. One other thing that we can do, okay, is the higher this little n value, the more magnetic field we get for a given current. Okay, one other thing that we can do is we can actually change what's inside of our electromagnet. All right, so if it's just empty space, okay, we use the permeability of free space, which is just the permeability within a vacuum. All right, if we put something inside there, it's kind of like with electrostatics, where if we put a dielectric, that's what I'm trying to say. If we put a dielectric in between like two parallel plates, we can increase the capacitance in between the two. All right, well here we use things that are ferromagnetic, things that have the potential to respond to magnetic fields. So things like iron, okay, is kind of like the best thing that's out there. If we put some iron inside of it, we can get a boost, all right, to our magnetic field by changing what's called the relative permeability. All right, so you will hear this sometimes. It'll say, oh, like there's a relative permeability of 200. Okay, so if I say relative permeability of 200, okay, all that means is that, well, you'd take your mu value would just be equal to 200 times mu naught, excuse me. Okay, so it's just like a multiplier. All right, so when we're solving for these things, you take the current, so 2 amps times the number of turns per meter, or 500 turns per meter, times the relative permeability, which would be 200 times mu naught, which is 4 pi times 10 to the negative 7th Tesla meter per amp. Okay, ultimately, you just got to do some practice problems with these. It's just plugging and chugging. All right, the putting the numbers into these equations is really the easy part. It's understanding what these equations are telling us. Okay, and that's the part that takes a little bit more thinking. Okay, so like I said, this is kind of brief overview of some of the basic configurations. All right, we have magnetic field around a wire, twist it into a loop. Okay, do a bunch of loops to get a multiplier. Eventually, it turns into like a cylindrical shape that we call a solenoid. The behavior changes. Now, the behavior for the solenoid is going to change when that length is proportionally a lot larger than the radius. So like the radius of this thing is teeny tiny. Okay, over here, whereas the length is long. So when the coil radius is less than a tenth of the length, we just start to call it a solenoid. How do we know which one to use? We use terms like the solenoid. Okay, so the questions are clearly stated. Look, it's a solenoid or it's a stack of loops. All right, so you don't have to worry about that. Okay, more than enough for one little screencast. All right, thanks for watching. I will see you next time.